Hey everybody, it's Mr. Molikash again with your next Calculus 1 video. Today we're going to talk about optimization, L'Hopital's rule, and antiderivative. So optimization, what does it mean to optimize something? Well, what it means is to find the best or worst case scenario of a changing quantity given a constraint. So let me talk about what I mean by constraint. Right. So we have what is the length of the radius of a cylinder whose volume is a maximum. So this is a changing quantity, right? This is the part to be optimized. And what's not changing is called a constraint. And so the height and circumference totaling 30 centimeters, that's called a constraint. Okay, so what's happening is this is going to be changing, which means we're going to do a derivative and find a maximum from our derivative using the first derivative test. The constraint is not changing, and we're going to use that to simplify our equation to be optimized. Okay, so first of all, we're talking about the volume of a cylinder, and we know the volume of a cylinder is pi r squared h. And we have this is going to be our changing thing, right, that we're going to try to find a maximum of. But the height and circumference of the base, right, the circumference is 2 pi times the radius, is 30. This is not going to change, right? So what we're going to try to do is we're going to use this equation to simplify this one. And we're looking for the radius. So what we'd like to do in this equation is get rid of the h, right, is to substitute h. So I'm going to use this equation that's not changing and solve it for h. And then I'm going to substitute that into this equation. So now I have pi r squared times 30 minus 2 pi r. And now that there's only one variable on the right side, I can say that my function is the volume that depends on the radius. It's a function of one variable. Okay. So now that we have our volume equation down to one variable instead of two, we can do a much simpler derivative. And if it were me, I've talked about this in videos before, I would definitely work smarter, not harder. So let's try to do the best method to find this derivative. And I think for me, instead of doing the product rule, I'm going to go ahead and distribute this out so that I can do the power rule, which is way easier, right? Okay, so pi times 2 pi is 2 pi squared r cubed. You might be weirded out by the fact that pi is multiplied by another pi, which is kind of bizarre, but don't worry. So what we're going to do now is find our derivative. So now we're going to do some calculus, right? We want to optimize this thing, and so we're going to find the derivative, v prime of r, and we're going to do the power rule because, well, that's pretty easy, right? So 3 times 2 pi squared is 6 pi squared, and we're going to do r squared. And we would like to kind of think about possible values of a radius. We know we're going to do the first derivative test to find a maximum, but the smallest value of the radius is 0, right? We can't have a negative radius. It just doesn't make sense in the context of the problem. So we're going to have r values on this number line. We're going to have v prime, and we're going to figure out what's going on with v. Okay. Now, in order to find critical numbers, there's no asymptotes or weird things going on with this particular function, so we can just set this equal to 0. So critical numbers happen when this 60 pi r minus 6 pi squared r squared is equal to 0. We can solve this by factoring. So we're going to factor out, let's see, 6 pi r, I think, is the GCF here. And so that would be 10 minus pi r. Now let's check and make sure I did that right. If I distribute this back, I get 60 pi r. If I distribute this back, I get 6 pi squared r squared. Okay, good. So algebraically, we can solve each one of these, and we get our critical numbers are r equals 0, which we already have up here, right? It's the left endpoint of our domain of the volume function. And the other radius would, if you set this equal to 0, I guess you get 10 over pi, right? 10 divided by pi. So that's going to be a critical number. And, you know, pi being around 3, I think it's probably safe to test some values, say like r equals 1, and something bigger than this, like r equals 5, right? So this would be 10 divided by 10, right, which is smaller than 10 divided by pi, and this would be 10 divided by 2. So I think we're safe to choose 1 and 5. Okay, let's put 1 into our volume derivative, right? Our volume derivative to see if the volume is changing in an increasing way or in a decreasing way. So if we put 1 here, we get a positive times a positive, which is a positive, so the volume is increasing. If we put 5 in here, we get 30 pi, which is positive, and then 10 minus 15 pi is negative, so positive times a negative is a negative. Okay. All right. So this means that when the radius is 10 over pi, that the volume is a maximum. So this is an applied way of using the first derivative test. And I think it's important to also talk about the fact that, in this context, radius cannot be negative. Okay? All right. So our next order of business is to talk about something called L'Hopital's rule. And L'Hopital, sometimes you'll see this with like a little caret over the O, and sometimes it's spelled with an S. So I think one of these is a French spelling and the other one is an English spelling. I'm not really sure. The S is silent, though. It's pronounced L'Hopital, okay? All right, so L'Hopital's rule is a way of using derivatives to find the limit of a fraction. Okay? And here's a really easy example of this. So remember early on in the course, we have this particular limit. The limit is x approaches 0 of the sine of x divided by x. Now, by direct substitution, if you put 0 into this, you get 0. If you put 0 into this, you get 0. And this is undefined, right? So if you were to evaluate this function at x equals 0, it's undefined, right? And in fact, because there's 0 on top and the bottom, we can say there's a hole in the graph and there's a removable discontinuity. So earlier we used the squeeze theorem to find this limit, but now we're going to use something called L'Hopital's rule. So let me tell you how it works. If you get a fraction, right? If you get a fraction and there's something called an indeterminate form. And there's many indeterminate forms, but the most common one is 0 divided by 0. Now, 0 divided by 0 is not a number. It's not a number. You cannot write that as an answer to anything, but it's the form of what the fraction might have evaluated at the x value where the limit is approaching. Okay, so if the numerator and denominator have limits at x equals 0, so obviously the limit as x approaches 0 of sine of x is 0, and the limit as x approaches 0 of x is also 0. If both of these exist, then what we can do is, instead of taking the limit of the original fraction, what we can do is take the derivative of both parts of the fraction. Now, I want to be really clear about this. I am not taking the derivative of the entire fraction. I'll write that out as a reminder in a moment. What I want to do is take the derivative of just the numerator, so that's cosine x, and the derivative of the denominator, okay? So this is not the quotient rule. I do not want to differentiate the entire fraction. I just want to do the top part and the bottom part separately. So now what I can do is I can say that this limit is equal to this limit, and I can find the value of the limit of the cosine of 0 as x approaches 0, which is the cosine of 0 divided by 1, which is 1 divided by 1, and the answer is 1. And certainly if you were to graph this function, you would see that the value of where there's a hole in the graph, where there's a removable discontinuity, is the point, the location x equals 0 and y equals 1. Okay? So why did this work out? Why did this work out? Because there's a rule that says if f of x divided by g of x takes an indeterminate form, then the limit as x approaches anything of f of x over g of x is exactly equal to the limit as x approaches a of f prime of x over g prime of x, if and only if the limit as x approaches a of f of x and the limit as x approaches a of g of x both exist. Okay? And there's a list of indeterminate forms in your textbook. Your book goes into way more, I guess, examples and different forms. So another, like, you can have infinity over infinity as an indeterminate form. 0 over 0 is the most common one. Infinity times 0. So like if one part of a function is growing rapidly and the other one is shrinking rapidly, like it's hard to know what the limit is if they are multiplied together, right? It's like who's winning the battle kind of thing. What you have to do in examples like this is make them into a fraction. Remember earlier in the video I said this rule only helps you find the limit of a fraction. So if your original expression is not a fraction, you have to make it into one. You have to write it as a fraction, which may seem kind of counterintuitive. Okay, all right. The last thing that I need to tell you about is what an antiderivative is. And so let's say that we have a function f of x equals x squared, right? So we all know by now that the derivative of this function is 2x, right? So soon and very soon you're going to start seeing notation of where instead of taking a function's derivative, we're going to take a function and find its antiderivative. So let's say that that x squared were the derivative of some function. What would the original function have been? In other words, what function's derivative is equal to x squared? This is like playing Jeopardy, right? Here's the answer. What was the question? And it's important to be able to work backwards in this manner to find something called an antiderivative. So the antiderivative of x squared would be the thing whose derivative is x squared, right? And if you've been thinking about this, there are lots of answers to this, right? But 1/3 x cubed would be one of them. 1/3 x cubed plus 100 would be one of them. 1/3 x cubed plus the square root of 100 would be one of them, because the derivative of any constant is 0, right? So there's lots of different antiderivatives for this particular function. Okay, so what we say about antiderivatives is capital F of x is an antiderivative of f of x if and only if capital F prime of x is equal to the function. So, for example, my previous thing there, right, if I had 1/3 x cubed, what is the derivative of this? The original function would have been 3 times 1/3, which is 1 x squared, right? So this means that 1/3 x cubed is it's not the only one, it's an antiderivative of x squared. Okay, so it's the backwards way of doing this. And soon and very soon, you'll learn some rules for finding antiderivatives. So let me just quickly tell you the one that works for the power rule, right? So if f of x is a power function, then that means that the derivative is where you move the power in front and multiply by the coefficient, so 1 times n is n, and then you reduce the exponent by 1, right? Okay, well, if f of x is x to the n and you want to work backwards and find an antiderivative, then capital F of x, well, let's think about what we did here, right? We multiplied by an exponent, multiplied and then subtracted 1 from the exponent. So the first thing we'd have to do to undo that process is add 1 to the exponent, right? And then instead of multiplying, we would divide, and we would divide by that increased exponent. So, for example, if n equals 2, then f of x is x squared, and capital F of x is x cubed over 3. And soon and very soon also, just to give you a little hint as to what's to come, you're going to see that there's a plus c after this because an antiderivative of 0 is any constant, right? So C stands for an arbitrary constant. And that's the reason why there are many antiderivatives for x squared. X cubed over 3 plus 100 would be an example. Okay. All right, we've got time for, I guess, more of a complicated example, I think, of L'Hopital's rule. So let me give you an example of L'Hopital's rule where something doesn't work out like we think it should. So let's see if we can find the limit as x approaches 0 from the right of x times the natural log of x. Now, first of all, our expression is not a fraction, row. So we're going to have to make it into one. Okay, we're going to have to make this into a fraction. I'm going to show you how to do that. The second thing is because the natural log's domain is limited to positive numbers. Remember, the natural log is only defined for positive numbers. There are no negative numbers, or you can't even put 0 because there's a vertical asymptote there, right? So no bueno. And if we were to try to evaluate this expression at x equals 0, we would get 0 times, and then the natural log of 0, remember there's like from the right, that is like negative infinity, right? So that means one thing is getting very, very close to 0 and getting small, and another thing is becoming very, very infinitely negative, right? And so they're sort of warring against each other, and we don't know what happens. Okay, whoops. All right, so here's how to deal with this algebraically using L'Hopital's rule, and also the reason why you can use L'Hopital's rule. So hang in there and I'll show you. The limit as x approaches 0 from the right, what we're going to do is we're going to put the natural log of x in the numerator of a fraction, and then instead of multiplying by x, we're going to divide by 1 over x. Now, let's stop and think for a moment that this fraction is the same thing as the green thing above it. It really is, isn't it? Right? If you're dividing by a fraction, you're multiplying by its reciprocal. So this is really like x over 1, right? And so you're dividing by the reciprocal, okay? So now at this point, we have, this negative infinity thing on the top, and then 1 divided by a very, very small number is positive infinity. And this is our indeterminate form, right? This is our indeterminate form that allows us to use L'Hopital's rule. Furthermore, the limit exists, right? The limit as x approaches 0 from the right of the numerator is negative infinity, or that's what we say. And the limit of the denominator is also positive infinity. So we can proceed. We can do this. And we can't evaluate this fraction, but what we can do is take the derivative of each of these particular functions, right? All right. And the derivative of natural log of x is 1 over x. And the derivative of 1 over x, let me do that over here. The easiest way to do that is to use the power rule, right? Write it as x to the negative 1, and then have negative x to the negative 2, which is 1 over x squared, but negative, right? So negative 1 over x squared. And then, okay, if we do some math here, if we do 1 over x divided by negative 1 over x squared, well, that's just the same thing as 1 over x times x squared over negative 1, right? And so this reduces with this, and then we get negative x, right? So our expression that we're finding the limit of really just kind of boils down to just being negative x, right? And so the answer to this would be 0, because we certainly can put 0 into this, right? So the answer is 0. So what that means is that if we were to look at the graph, and I don't have Maple on this particular device I'm shooting a video on, so I'll use Desmos. But if you were to look at the graph of the function x times natural log of x, you'd see that near x equals 0, it'd be near the origin, okay? So let's do that real quick, and just so that you can convince yourself that all the algebra that I just did is correct. All right, so we'll make this real big so you guys can see. So x times the natural log of x, it's got this wonderful curvature to it. It's not defined for any numbers that are negative, so that's the reason why we had to approach 0 from the right. And if we zoom into this, you can see that there's this thing going on, and you can kind of like trace along the graph here. And by the time you get to the origin, look what happens. At x equals 0, the function is undefined, right? That's because natural log of 0 is undefined. However, you can see that the location of this ordered pair that would be there if it existed, that's the location of that removable discontinuity is 0, right? So graphically, we can say the limit as x approaches 0 from the right of our function is 0. But if we were to plug 0 into it, you would get 0 times negative infinity. So that's the reason for having to use L'Hopital's rule. Okay, so that's all we have time for right now. There are lots and lots of examples in Patrick JMT's site, which I will link for you in my folder if you're one of my students. But I want to give a shout out to Patrick JMT, who has some really good videos for optimization problems. And if you need help on L'Hopital's rule, there's a wealth of resources there. There's some harder examples where, x is approaching infinity and that kind of thing. And antiderivatives is kind of the bridge between differential calculus and integral calculus. So we're in our next video, we're going to start talking about why we have this thing called an integral in calculus and what it's used for. So until next time, have a great week.